astronomy, because it's quite an interesting story. Radio astronomy in most countries in the world was started by people who had worked in radar during the Second World War. And at the end of the Second World War, they used radar receiving equipment, turned it to the sky to see if they could pick anything up. They did actually suspect the sun was a radio source. They wondered if there was anything beyond the sun that was a radio source. This particular image is of the big radio telescope at Jodrell Bank. It has just been made a World Heritage Site, so they can't allow it to fall down, which has financial implications for the university, but minor detail as far as we're concerned. So these radio astronomers turned their primitive radio telescopes to the sky and started picking up some quite strong signals, not just from the sun. And they managed to position these signals and then said to the optical astronomers, what is there at such and such a position? And the optical astronomers would say, well, there's something that looks a bit like a star, but it's not like any kind of star we've known. And so these things were called quasi-stellar radio sources, or quasar for short. They got some information, got some redshift data, which implied that the objects were very, very far away. And that was quite alarming to them. I might tell you that bit of the story separately. But they're quite strong radio sources. And if they're distant, you'd expect them to be really rather faint. So what's going on, basically, was the question. I started life in the north of Ireland, had some of my education in the north of England, did my bachelor's degree in Glasgow, and then quit the north and west of the country and came south to Cambridge. And it was like coming to another country. I became quite conscious that I hadn't a proper background. I was from the north and the west. I had an accent that still is north and west-ish. And I think it's probably fair to say in Britain there is a perception, at least in the south, that there's this gradient in the country. And I had gone uphill, so to speak, on this gradient. I quickly thought they'd made a mistake admitting me. Everybody seemed very, very clever, very confident, quite confident in their right to be in Cambridge, and very suave with us all as well. And I thought, they've made a mistake admitting me. They're going to discover their mistake and they're going to throw me out. This we now know is classic imposter syndrome, but we didn't identify it or name it 50 years ago, 60 years ago. So typically when somebody gets imposter syndrome, and this will happen in Cambridge as well as Oxford, the student will say, they've made a mistake admitting me, I'd better leave before they throw me out. And within the first 2 days of the academic year, they're gone. Well, I'd had a bit of a battle to get where I'd got, and I wasn't going to walk out of my own accord. But I did know that they'd made a mistake admitting me and that they would throw me out at some point. I decided what I would do was work as hard as I could so that when they threw me out, I wouldn't have a guilty conscience. I'd know I'd done my best. And I'd recommend that to anybody suffering imposter syndrome. Within the first week in Cambridge, new radio astronomy graduate students, theoreticians accepted, were each given a set of tools. And this is my set. They are not microwave electronics tools. These are full-size wire working tools. And they got used a lot because I spent the first 2 years building a radio telescope. This is near the end of the building. My particular responsibility was all the cables and all the connectors. And I've been working through the winter weather in that little red and white hut behind me, or in the one in the distance, middle distance, with cables laid out between the two. And I work in each of the huts, putting plugs and sockets on the cables. And here we're checking the impedance of these cables to make sure that the connections are good. I have a slotted waveguide in front of me. It was an enormous radio telescope, covered an area of 57 tennis courts, and it took 6 of us, best part of 2 years to build it. My particular responsibility, whoops, something's gone wrong. Okay. My particular responsibility was all the plugs and cables. This is a picture of the finished article. It looks homemade. It is homemade. It actually consists of rows and rows and rows of antennae made of copper wire, and you can see the copper because of the nice bluey green color it is. There's about 200 kilometers of wire and cable in that thing. What was it meant to do? The diagram on the left is a bit sketchy, but I hope it will help you understand. If we look at the top half of the diagram first, there's a quasar at the top. It's actually very, very distant, way off the sheet of paper, way off the slide. But radio signals from the quasar come down towards the Earth and have to pass through the solar wind, the stuff that fills the space between the sun and the planets. This solar wind is an ionized plasma. There are free electrons in it, and it's not absolutely smooth. There are, quote, clouds that have higher electron density than other areas. And it acts a bit like these clouds act a bit like a diffraction grating, and the incoming beam is spread out. The clouds are also blowing past because they're part of the solar wind that's streaming out of the sun. And so a radio telescope down the bottom, if we're dealing with a compact source, sometimes sees it brightly through the gaps between the clouds, and sometimes sees it more faintly, and sometimes in between. And the bottom half of the slide shows you the kind of signal that you pick up from a compact object like a quasar when you look through the solar wind. You have to look through the solar wind. We can't escape it. It varies. It fluctuates in brightness, and you might see the 1 second time mark to give you an idea of scale. So it's quite a fast twinkling or scintillation. If your radio source is much broader, then you see it through several clouds and several gaps, and the clouds blowing past don't produce the same amount of twinkling, of brightening and dimming. So it's only a compact object that will show this kind of changes in brightness. And it's a very neat way of picking out compact objects, or quasars. At the time I started, there were only about 20 quasars known, and it certainly wasn't a big enough sample. By the time I'd finished, the number had got up to about 200. The twinkling is a bit like, not exactly like, but a bit like what you see if you lie on the floor of a swimming pool on a sunny day and look upwards. You see bright bits and dark bits as the ripples focus the sunlight and unfocus the sunlight. In the case of the visual, there are caustics. There are not caustics normally in the radio, and the pattern moves as the wind blows the waves by. When these quasars were first found and the optical astronomers were trying to work out what they were, a key person was an astronomer called Martin Schmidt, a Dutchman working in California. One of the first quasars was called 3C273, and they got an optical spectrum of it, and he could not make sense of it until he realized it was the spectrum of hydrogen with a very large redshift. You may have seen the spectrum of hydrogen in a lab, diffraction grating. There's a prominent red line and some blue and some violets. Now, the snag about a large redshift is because of the way the universe expands, it implies that there's a large expansion velocity away from us, which implies these things are at a great distance. And if they're at a great distance, they ought to be faint, but they weren't. So what the heck are they? When Martin Schmidt realized that they had this large redshift and therefore were distant, it's reported that he went home to his wife and said that night, something terrible happened at the office today. He was really alarmed, shaken by the large redshifts that he was measuring. So I think I've said most of this. I observed for 6 months. I found about 180 more quasars, and that was the bulk of my thesis, but there was something else as well. At that time, the University of Cambridge had one computer. It occupied a large room. It was full of vacuum tubes, valves, and it had memory comparable to your laptop. And clearly, very few people could get time on it. And we did not have time on it. Our data came out on long rolls of paper chart. And this slide shows me analyzing some of the paper chart. Now, there was 30 meters a day of it. I scanned the sky every 4 days. So that's 120 meters per sky scan. And in the 6 months I observed, I had over 5 kilometers of this paper chart. I got used to identifying the quasars. I got used to identifying radio interference because a big radio telescope like that will pick up radio interference very nicely, thank you. In those days, the interference could be badly suppressed cars, anything that sparks, arc welders, sparking thermostats, sparking power lines. And we even had trouble from pirate radio at one point. Now, in amongst this 5 kilometers of stuff, there were the twinkling quasars, the scintillating quasars, there was this human-made interference, and there was just occasionally something else. And this particular slide shows you interference towards the right hand, well, center right, and the other signal. And you can probably see that the two don't look exactly the same. The one in the middle, the spikes go up and down. The one on the left, the spikes go mainly up. The one in the middle, you can see space between the spikes. The one on the left, certainly at the left-hand end of it, there is no space between the spikes. Incidentally, when you make that kind of comparison, you're actually doing a Fourier analysis. So you've unconsciously done Fourier analysis. When you say spikes go up and down, or spikes just go up, you're talking about the amplitudes. And when you say you can see space between the spikes, or you can't see space between the spikes, you're talking about the frequencies that are present. And that's Fourier analysis. What frequencies are present with what amplitude? So this peculiar signal on the left didn't look like a scintillating quasar and didn't look like interference. I couldn't classify it. It often wasn't there, but it was sufficiently troublesome that it stuck at the back of my mind. And because it stuck at the back of my mind, whenever I came across it, or at least one occasion when I came across it, my brain said, you've seen something like this before that you couldn't classify, haven't you? You've seen this before from this bit of sky, haven't you? And then it's easy because the charts, paper charts, each correspond to a different declination, which is like latitude on the sky. And I have them filed by declination. So you pull out all the other charts that cover that strip of sky, and compare. And quite often the thing wasn't there, but when it was there, it was always at the same position. Human brain is actually very good at retrieving information. This signal occupied about 10 parts in a million of the chart paper that I was analyzing. I showed it to my thesis advisor, who said, yeah, well, great, but it only occupies about 0.5 centimeter. We can't see what's going on. We need an enlargement. And with this technology, enlargement is quite easy. You run the paper faster under the pen and it all gets spread out. An enlargement. The snag is I couldn't leave the pen recorders perpetually on the faster speed or they'd run out of paper every 20 minutes. So I had to go out to the observatory each day just before this thing was due to be observed and switch to high-speed recording. And I did it for a month and nothing happened. And of course, it was my fault. My thesis advisor was furious. And then finally one day I got it and in comes this signal. The lower trace is man-made time pips, 1 second markers. And the upper is the thing, which my supervisor subsequently has labeled as LGM1. It's a series of pulses. They're about 1 1/3 seconds apart. And even when they get so weak you can't see them, they come back on beat, on phase. So what the ... is that? Incidentally, you know that labeling LGM1 is added afterwards. When you just have one of something, you don't label it LGM1. It's only when you've got more than one, you go back and relabel the first one as number 1, and the second is number 2, and so on. Well, big radio telescope could pick up a lot of radio interference. Was it that? No. It kept its place amongst the stars, and the sidereal day is 23 hours 56 minutes, not 24 hours. So it's not somebody driving home from work because they're getting off work 4 minutes earlier a day, 28 minutes a week, and this has been going on for a month or two. Well, maybe it's faulty equipment. We got a colleague who also had a radio telescope and its own receiver working at the same frequency, got them to look and see if they could see it, and they could. So it wasn't a fault with our equipment. But it was a big puzzle, because you see the pulses are quite steep, which means the object's quite small, but they kept to that beat period, that period very accurately, which implied they were big. So they're big and they're small. Then we got a dispersion measurement. You'll have seen dispersion in the optical. That's what gives you a spectrum. There's also dispersion in radio waves. The high frequencies travel at a slightly faster speed than the low frequencies. It's caused by electrons, and the more electrons the radio signal goes past, the more dispersed, the greater the separation between the high frequencies and the low frequencies. So a colleague took 2 of my receivers, tuned one of them up in frequency slightly and one of them down in frequency slightly. And after a lot of false attempts, managed to see that the pulses came slightly earlier in the higher frequency. And by measuring how much earlier, he got an estimate of the distance, put it at about 200 light years, which is beyond the solar system, but well within the Milky Way, quite close in the Milky Way. So we were wondering, hoping we were wrong, but wondering if it could have been little green men, so to speak. If it was little green men, they'd probably live on a planet, and that planet would orbit their sun, and we should be able to see the Doppler shifts on the pulse period as they orbited their sun. We weren't finding a Doppler effect except for the motion of the Earth round the sun, because the observer moving can also give a Doppler effect. And so we weren't making a lot of progress. And then I found a second, a third, a fourth. And this begins to look like some kind of stellar object and look less and less like little green men. There wouldn't be four lots of them, all choosing to signal to planet Earth and all using a similar technique. It had to be something natural. Tony, my supervisor, was inclined to think it was something vibrating. An alternative possibility was something rotating. And we now know that the rotating model is right. We published the paper and the press took a huge amount of interest, and we had lots and lots of interviews, Tony and I, and they would ask Tony, my supervisor, about the astrophysical significance of this discovery. And then they turned to me for what they called the human interest. How tall was I? What were my bust, waist and hip measurements? How many boyfriends did I have? And photographers would ask me if I could undo some more buttons on my blouse. It was really horrible, horrible, horrible. But as a grad student who still has to finish a thesis and get her degree, I didn't feel I could make a lot of fuss. One of the interviews was by the science correspondent of the Daily Telegraph. His name was Anthony Michaelis, and he asked what we were going to call these things. Now, we'd given some thought to this. Were they pulsating radio sources, or were they pulsed radio sources? Pulsed implies as maybe an agency. Pulsating suggests something more natural. So he said, yeah, they're pulsating radio sources. And he said, no. What about a short name? What about pulsar? A bit like quasar. So pulsars they've become. And it was the science correspondent of the Daily Telegraph that created that name. So what are these things? They are stars that spin, as all stars do. They have a very strong magnetic field, which is inclined to the rotation axis. And somehow, with quite a lot of hand waving, a radio beam comes out from the magnetic poles, focused by that conical magnetic field shape. And if that beam shined in our faces, we see a pulse. And if it doesn't, we don't. So we perhaps only see 10 or 15% of all pulsars. They are a bit like lighthouses. And there is incidentally a suggestion they could be used like lighthouses when we start traveling through the galaxy in spaceships. They're very small, very dense. They're rich in neutrons, so they become known as neutron stars as well. With all that mass in a small volume, they've got very strong gravitational fields. They've also got very strong electric and magnetic fields, and they're spinning quite fast, typically about once a second, but some go maybe 100 times faster than that. And we believe they're formed when a massive star explodes, what's called a supernova explosion at the end of its life. And these things were the core of the star that exploded. And in the explosion, the core gets shrunk right down to be one of these neutron stars. And they're primarily observed as radio emitting objects, but you can see them at some other wavelengths. You can see them in X-rays and gamma rays. So we've got probably over 3,000 radio pulsars now known. Only about 20 of those are visible, about 100 you'll see in the X-rays, and about 200 in the gamma rays. This is an unusual pattern. Usually the smallest number would be gamma rays, the next smallest X-rays, and the most visible. So they're clearly not typical stars. We think about 10% of them are in binaries. We know of one in a triple system, and we know of a few with planets. And there's probably 100,000 in the galaxy, but that's a bit debated. We've still not got a good handle on that. They're formed when a large star, particularly big star, explodes at the end of its life. It's what's called a supernova. 90 to 95% of the star is ejected. The rest of it is collapsed down to be one of these neutron stars. And one of the most famous supernovae that we've had was in a nearby small galaxy called the Large Magellanic Cloud. And I've got two photographs here. The left-hand one is before. You can see a mass of glowing gas up top left. You can see a lot of pink stuff. That's hydrogen gas glowing in its red spectral line. And there's a fair spattering of stars. And one inconspicuous star in the bottom right is pointed out with an arrow. Just to be absolutely clear, the arrow was added after the photograph was taken. There aren't arrows up there in the sky telling you which star to look at. And in the after photograph, you can see that that tiny, tiny star has exploded and become very visible. It's what we call a supernova. And we expected that in the core of that explosion, there would have been one of these pulsars formed. But we couldn't find it, and we couldn't find it, and we couldn't find it. Just recently, from the University of Cardiff, primarily, using a telescope in Chile called ALMA that works at millimeter wavelengths and observes dust, they've looked right in the center of this supernova explosion. There's some dust there now, and they see the very central part of the dust glowing hot, as if it was illuminated by a neutron star. So we suspect there's a neutron star there, but it perhaps is not pulsing or not shining the beam our way. Another thing that pulsars have done for us is they've solved the problem of the Crab Nebula. This is the remains of a star that exploded in 1054 AD. It was observed by the ancient Chinese. And as a star that exploded on a definite date, this glowing debris ought to be fading. The glowing debris is not fading, and one of the very big problems was, why is that nebula not fading? We now know that there is a pulsar in its middle left over from the supernova explosion, and the pulsar is giving energy to the gas, keeping it glowing. The world continues to build bigger and better radio telescopes. This is one in China. It's basically built in a bowl in the ground. It's 500 meters across, and it's been working for a few years now, and it's discovered, I believe, 240 more pulsars. This is another big radio telescope in Canada, in the Rockies. It's made of 4 cylindrical troughs. You don't need to go into the details. It's very recently started operation, and it's going to be good for studying pulsars. One of the advantages of having discovered pulsars is every so often somebody comes up to me and says, you know, I nearly discovered pulsars, and tells me the story. And I think it throws quite a bit of light on how science research actually works. So if you're all still with me, I'd like to take just a few minutes and explain some of these stories about how pulsars were nearly discovered. The first one is a way back in 1957 in Texas at the McDonald Observatory, where the telescope there had to be open to the public one night every month. And it's the public viewing night. The telescope is set on the Crab Nebula, that nebula that I've just shown you. In fact, it's set on the center of the nebula where there was a slightly peculiar star. And members of the public would step up to the telescope and say, ooh, wow. I don't know what words they used back then, probably not cool, but the equivalent of that, whatever there was in 1957. One young woman steps up to the telescope and says, that star's flashing. Now, we know now that there is a pulsar in the center of the Crab Nebula, and it does flash. It flashes about 50 times a second. This is near the limit of what the human can see. But some people can, and apparently young women tend to have some of the best acuity, and they're more likely to see it than anybody else. The night assistant started explaining about the way stars twinkle, and she said, no, no, no. I hold an airplane pilot's license. This is 1957, and a young woman holds an airplane pilot's license. She says, my job is to fly aircraft from the manufacturer to the customer. I fly at night. I know the night sky quite well. I know about stars twinkling. That star is flashing, not twinkling. Elliot Moore, who was just graduated and was working as a summer assistant, believes that she saw the Crab pulsar. It's near the limit of what the human eye can detect, but it's possible. And he regrets that nobody had the initiative to follow up. The argument was that there weren't any instruments available. He doesn't believe that. He's told this story to every generation of students he's taught thereafter. If she'd been believed, the pulsar story would have been very different. Here's another instance where the pulsar story might have been very different. It's as late as 2007, so a lot of pulsars are known. And Australian radio astronomers suddenly get an email from a gentleman in the USA called Charles Chisler. He's the gentleman furthest away from us in the photograph. And he says, as a United States Air Force technician during a one-year period back, that's during the Cold War, he's at the ballistic missile early warning site in Alaska, basically looking for Russian missiles coming in. He says it was a bit boring, there wasn't a lot to do, and he played around with the equipment when everything was quiet. And he discovered 14 pulsing signals on our extremely powerful radars. He'd done an undergraduate degree, he'd done an astronomy course, he knew about right ascension and declination, and he took the trouble to record the right ascension and declination as well as he could of these 14 pulsing radio signals. He's just discovered the online pulsar catalogue that the Australians set up. And he's over the moon because one or two of his sources, in particular the Crab Nebula, are in that catalogue as having pulsars. Now, he was doing highly classified job. He wasn't allowed to publish. And so this information remained hidden until 2007, by which time quite a few pulsars had been discovered. But if it had not been classified information, we might have discovered pulsars back in 1967. And another 1967 discovery, or failure to discover, Sue Simpkin, who now works in radio astronomy, was doing ultraviolet spectroscopy. She had time on a telescope, and a Dutch professor, Lo Vulture, in the other photograph, asked her, excuse me, to take an ultraviolet spectrum of that funny star in the Crab Nebula. So Sue took the spectrum. She said the spectrum of the nebula was lovely. The spectrum of that star was dull, but she could see it flickering. Now, Sue Simpkin was brought up in Canada, where the electric mains frequency used to be 50 hertz. Some people can see 50 hertz. They got very annoyed if they lived in Canada. Sue was one of them. And so we believe that she actually saw the Crab pulsar, which goes at close to 50 hertz. Lou Vulture at the time didn't believe her, but when pulsars were discovered, he was man enough to say she was probably right. My last story is from radio astronomy, and although the person involved is no longer on this earth, He was always very embarrassed by this, so I'm not going to name him. He was one of a group making a survey of the whole of the radio sky at a frequency of 408 megahertz. It's been a long job. They got time on large telescopes where they could, when they could, 1 week here, 10 days there. And in this last week or so, they're filling in 1 or 2 gaps in the map. It's pen recorder technology, and one of the pens is misbehaving. And one day at about 3 o'clock in the morning, the worst time of day, that pen recorder starts misbehaving. The pen starts going weep, 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 weep. And the observer says, damn, and thumps the pen recorder. This is the way you used to cure problems with lots of equipment. Just don't do it with your laptop. So he thumps the pen recorder and it stops going wheep, wheep, wheep. And he says, thank God, puts on his coat and goes back home to bed. And he did not make any record in the logbook. If he'd made an entry in the observing logbook, he could have claimed prior discovery of a pulsar 0329 plus 54. So there were a number of near misses before pulsars were actually discovered. I think the factors that led to the discovery were I had my own telescope and receiver, and I made it my job to understand how they worked. But I think a bigger factor was this imposter syndrome. Remember that I was sure I was going to get thrown out because I wasn't bright enough. And I decided to work my very hardest so that when they threw me out, I wouldn't have a guilty conscience. I was being very, very, very thorough. And as a graduate student, you have time and space to follow up anomalies. This was one of the few surveys that operated with quite a short time constant. So in modern technology, we're in a new area of phase space. We weren't aware of anybody else actually doing this kind of work either. We now know that that wasn't the best frequency for observing pulsars. The first source was not the strongest, but nonetheless, we found them. If you have to publish a really dramatic stroke crazy result, it helps if you have a good address. And the University of Cambridge is a good address. So editors of journals were inclined to believe us. This was not one of the targets of the program, one of the objectives. These days, there's a tendency for research funding bodies to assess work on whether it achieved its targets or not. And my final point, and where I will end, is that these days we're getting so much data coming out of telescopes, the data has to go straight into a computer and be sorted and analysed by the computer. There's far too much for a human being to handle. The snag is you probably only program the computer to look for things you're fairly certain exist. So the unexpected might not be discovered. So I will finish there. We have a small pulsar group in Oxford, lovely group. The subject remains immensely exciting and intriguing with a lot of questions unanswered, and it has been huge fun. And thank you for your interest and your attention. I'll finish there.
Thank you so much. Thank you so much. That was such an interesting talk. Julian, will you take over the Q&A session?
Yes,
Amazing.
I will. Of course, I just want to carry on with what Oscar was saying. It was a really great talk. Some great things mentioned. I really like how you brought in your experience with imposter syndrome and how you were coping with that, and it's obviously quite applicable for sort of people at university, because when it's really, I think, felt. So it was really nice that you mentioned your personal experience with that. Before we move on to the Q&As, I just want to mention about next week's talk, which is Christopher Szorensky. Hopefully I'm pronouncing that correctly. And the title is Scaling Down the Laws of Thermodynamics. Check on the chat for any questions. Also, we had about 130 people in the call at our max. That's what I noticed. So including Zoom and on YouTube as well. It's around about 130.
So just to everyone, if you have any questions, feel very free to just unmute yourself, potentially, or post it in the chat.
Mm-hmm.
That also includes the YouTube chat. We are looking at that as well. Well, if I may start off another little question. So you mentioned that the origin of pulsars was from how should we say, like a sort of a non-scientist, a sort of the Daily Telegraph, a science correspondent. Do you know if any other names have come out from people not doing science? Because it was a pretty funny story.
Yeah, there might be one or two others. Doesn't often happen. Scientists usually, get in there first before other people get to hear of it. So it quite often is named. And we've got more alert to providing catchy names as well. So that I think likely the scientists will name it.
Okay, fair enough. So going from a chat from YouTube first. So at the end of your talk, you mentioned about the Oxford Pulsar group. What are some of the recent sort of developments that have come out from that, and what's being worked on at the moment?
Right. Well, there are several new radio telescopes. There is a big one. Well, we're working towards having a radio telescope that has a collecting area of a square kilometer. This will not be a single dish. It'll be a whole lot of smaller dishes that add up a square kilometer. And part of that's going in South Africa and part of it's going in Western Australia. And the South African prototype for that is now up and functioning and delivering really, really interesting stuff. It's called MEERKAT, MEERKAT. The KAT bit stands for Karoo Array Telescope, which is what there was before there in the Karoo. They've enlarged it, they've made it bigger, and in Dutch, the MEER means more. So it's the bigger KAT. And MEERKAT is one of the telescopes we're using quite a bit in Oxford. Sometimes means you have to go to South Africa to make some observations. Sometimes the observations just come to you over the internet, which is much more boring.
Yes, I can imagine. Thank you so much for that. I have one question. Does low Earth orbit communication satellites interfere with your searches for pulsars?
Those satellites will be a huge problem for optical astronomers. Absolutely enormous, drastic, devastating, end of the world. Because you can't take a photograph of a star without getting 1 or 2 or 10 of these things zipping by. They may also be a problem for the radio astronomers. It depends how well screened they are from, will they produce radio interference, send it out into space, or will that all be kept inside a metal canister? We've yet to find out, but for astronomers in general, these Starlink satellites are a real nightmare.
Post-apocalyptic satellites, clearly.
Yeah.
So you mentioned, if I remember, 20% of the pulsars are within the visible spectrum. Are there any ones that, a sort of civilian, sort of amateur astronomer might be able to see? I can imagine that's quite a nice sort of experience to get into
Yes.
astronomy, to notice
Yeah.
these.
The one in the Crab Nebula is fairly accessible, as long as you can put it going 50 times a second. You're going to need some clever electronics that will do some gating or something like that for you to see the pulses. As a steady object, but you really want to see it pulsed. And so I think you're going to have to do some gating or something clever like that. And it's non-trivial because the period that you observe for that pulsar depends on the motion of the Earth. There's a Doppler shift due to the motion of the Earth, which of course keeps changing as the Earth moves.
Yeah. I definitely have to get back into astronomy. One question in the chat, which is a bit more of a tangent. Do you think particles like tachyons, which are supposedly meant to travel faster than the speed of light, if you could weigh in your personal opinions, do you think they exist? You have any?
I don't know. I'm not a theoretician. My understanding is that they shouldn't, put it that way.
Yes.
Astrophysicists in general are beginning to get more into particles, but it's known things like neutrinos. So there's
yes, yeah.
what's called astroparticle physics as well. But I don't think tachyons are featuring there.
Well, not yet at the moment, but hopefully in the future. One question which I think would really resonate with your talk is what would you say to encourage young female researchers in sciences?
I can really only speak for astronomy and physics, to be honest. There are actually quite a lot of women in the biological sciences, so I think it probably feels very different. It's, I think, very important for physics that lots of people with different backgrounds do research. It's been very interesting work by a management company called McKinsey in the United States. McKinsey shown that the most successful businesses are those with the most diverse workforce. So not only diversity in gender, but diversity in race and economic background and all sorts of things like that. Diverse groups are harder to manage, but if you have somebody who can manage that kind of group, then it's likely to be more successful and more robust than a group that's more, shall we say, monochromatic. So I think that's a very strong argument for having gender diversity, racial diversity, diversity of background, every dimension you can think of in physics research or in any research.
Yeah, thank you. I definitely have to read the article on McKinsey. It'll be interesting. Going back to some of the theoretical things we mentioned with tachyons, what about any comments on dark matter or dark energy and dark, other?
Yeah, well, dark energy and dark matter are big issues. We're clearly missing large chunks of what's in the universe until we actually work out what these things are. I suppose that we can say at least we know that we're ignorant at the moment.
Yeah, which is
there are searches
sort of nice.
for both going on, to be sure. But as yet, I don't think not aware of any results, anything that can be reported other than saying Yeah, we know we ought to find these things. We know they're there to find, but we don't know what they are.
Yeah. Going back onto the main things with pulsars, could you tell us something about what generates the culminated radio beams from the radio pulsars?
How the radio signal is produced is clearly very, very extreme physics, which I don't claim to understand, and there's probably only a couple of people in the world who do understand. But you're dealing with highly relativistic, high-speed stuff, high temperatures, high densities, large magnetic fields, rapid rotation. You've got every extreme at once thrown into the mixture. So it's not easy to explain. Yeah, I think I probably have to stop at that point. The physics is foul because of all the extremes happening at once. You can make no simplifying assumptions.
Extreme physics of stream effects. With pulsars, is there any way to say what might be a pulsar without necessarily like observing the radio pulses? Is there any way to sort of detect pulsars without seeing their pulses? Because you mentioned that they've come in like the Crab Nebula. So is it true that all nebulas will have pulsars?
We expect many supernova remnants to have pulsars, but of course the chances are that the beam is not swung over the Earth, that it misses the Earth. So we're only seeing 10% of all the pulsars, because the other 90% don't face us, so to speak. But looking in supernova remnants is the sensible thing to do, because we do believe they're formed in these supernovae, these exploding stars.
Yeah. So presumably if you're looking for new pulsars, you usually look at supernovas and then try and find a pulsar rather than the other way around, or just a random searches.
One of the complications is that in the explosion, the pulsar can get given quite a kick, and it goes tramping through space at a considerable speed, and it may have moved away from the supernova remnant. So just focusing on the remnant, I think, is too limited. It's better to scan the whole sky and look for pulsing objects rather than to focus on a particular kind of object in the sky.
The explosion they're going to move. I didn't think about that. So we have a viewer in from Kenya. It's very nice to see.
Right.
And they were really intrigued by, you mentioned that they could be used as space lighthouses. What other practical use can research on pulsars be, / what use have they been?
I doubt if they've got much other uses for humankind, to be honest. We do recognize, though, that the explosion that creates a neutron star will also generate quite a lot of the heavier elements further up the periodic table. I think probably gold comes from supernova explosions, so I'm not sure that gold's useful, but it's very nice.
Well, there's a little bit in all of our computers that are making this possible. So so it's very useful indeed.
Yeah.
I believe. Or one other question. Could you maybe comment on why these pulsars usually only emit radio waves and not other part of the EM spectrum?
Yeah, that does.
Or do they even admit other parts of spectrums?
Some of them do emit, particularly the younger ones that seem to be more energetic, the more recently formed ones, find at higher frequencies than radio. And we suspect that as they age, they retreat down from the X-ray and the optical into the radio only. So they're primarily radio objects.
But presumably the new pulsars, you could see a bit of their sort of black body radiation, I assume. Is that what the...
I'm not sure. Don't think I know of any instance of the black body radiation being seen. You're looking for the pulse stuff. And it's much easier to pick a pulsed signal out of noise than to pick a weak, steady signal. So people have tended to focus on the pulsed bit.
Yeah, which makes sense. We've got a question from someone on the committee. What's your main piece of advice to someone aiming to get a career in astrophysics research? And also on that note, what books would you recommend for aspiring physicists?
I think if you want to do research in any bit of astrophysics, you should get a good physics degree to start off with, a standard physics degree. You can pick up the astronomy later, but it's really important that you understand physical processes. So that's why I'm emphasizing a physics degree. Not sure about books, to be honest. I'm tending to use the web more these days and look things up there.
Yeah, it's sensible. The web becoming the all-knowing, all-powerful object that it is.
Yeah.
I don't know if this is, there's one question that quite intrigued me, and I don't know if this is a coup controversial for you to like comment on, but regarding the Nobel Prize controversy in 1974, Peter Suman has a question about whether you could give your view on it and what their explanation was for not awarding you the prize.
Well, I don't know the explanation because I wasn't party to the discussions that went on.
Yeah.
But
but you...
Yeah. Back then, students were kind of an add-on. It was the academics, the tenured academics who mattered. So students quite often didn't feature in these kinds of prizes. So I'm sure that was part of it. It was a very important Nobel Prize because it came from the physics committee. There is no astrophysics or astronomy Nobel Prize. And the physics committee had plenty of physicists to give the prize to and didn't usually look at astrophysics. So the fact that they noticed the discovery of neutron stars and made an award there was very, very significant. And I knew it would open the door to a number of other astrophysicists getting the Physics Nobel Prize. And that has indeed proved to be the case, indeed, where the two people who studied the motion of stars close to the black hole in the center of the galaxy got the Nobel Physics Prize. So since 1974, a fair number of astrophysicists have got the Nobel Prize, the Physics Prize. And I think that's quite right. Astrophysics is really part of physics.
Okay, thank you so much. That was really enlightening to hear what your viewpoint is.
One quick question. Is a radio telescope you built in the 1960s still operational?
No, it has fallen down, needless to say.
Oh,
Over
what a shame.
watered. And at one point, when the price of copper was very high, this was after we'd stopped using it, somebody came in one night with some wire cutters and took away all the copper.
Yeah, I can see that being
The radio telescope without its copper antennae is not a radio telescope.
It isn't. It isn't. Oh.
Then I don't know, Julian, do you want to continue on with the questions? Otherwise, even with the delay for the technical difficulties, which I do apologize for, I think we've gone through quite a bit.
Yeah, questions.
So
yeah, I mean,
you probably also have things to get on to, Jocelyn, in your day. But it was a very wonderful talk. Do you want to do maybe one last question?
Yeah. We'll do one last question. What is the range of pulse rates that are seen in pulsars?
Right. They seem to switch off when they, well, I'll start again. They're born spinning quite fast. They've got quite a fast pulse rate. And the spin gradually slows, and so the pulse period increases. And when they get to something like 5 seconds, 10 seconds, they seem to die off. Presumably there isn't enough rotational energy, not enough oomph.
Yeah.
Generating a healthy radio beam. When they're newly born, they're going at millisecond rates, maybe 5 milliseconds, something like that. They gradually slow over a lifetime of perhaps a few million years, something like that.
Okay, well, thank you.
Thank you very much.
Well, that was it was all very good, and like I say, thank you so much for dealing with all the technical difficulties. You handled them really well. It was really brilliant. Thank you, really brilliant.
So thanking you.
Yeah, I will stop the live stream now. And I guess I don't know how much longer you want to stay, but we could go over to an informal, just have a chat now if some people want to join, and if you have time.